Greetings, gentle readers. Reading Foundations today, November 14, 2025, with Ross Finlayson, my little library here. What I'm going to be reading about today is JPEG, Joint Photographic Experts Group, JPEG standards, and the ideas of image file formats, their internals, and so on. So let's take a look at the box of the books and see what will be being read a bit today. Because what I saw last time, so I was closing the previous episode of Reading Foundations, was that there's a big book here on JPEG called JPEG2000, and there might be the other ones too. Because there's basically 2 or 3 JPEG books. There's JPEG, and there's JPEG2000. And then there's one maybe about JPEG-LS, and then there's some other books that have relevant ideas and issues that are pretty much focused to make an example use case or study of JPEG. And then that is then after the ISO standards. Now I forget exactly what this series is of the International Standards Organization standards for JPEG, and there's the Joint Photographic Experts Group, and there's a motion picture experts group, JPEG and MPEG, the motion picture variety with sound also. That the JPEG and MPEG represent a series of file format standards for imaging data. For the continuous tone imaging is largely what it's for. So continuous tone means that it varies in kind of a continuous way compared to like discrete tone or not continuous tone imagery, which has blocks like text or otherwise things like just graphical elements themselves. So that's what it's about. And JPEG is one of the most common and ubiquitous standards in the world of consumer electronics and multimedia today. So almost all cameras deal with it. Almost all aspects of the digital video use the same sorts of routines to compress the data, and so that it's a bit stream. It's just a sequence of zeros and ones. It's an uninterpreted octet sequence or sequence of bytes. Then after being sent over the wire or a differential pair, or as via from an antenna from the pulse code modulation, or otherwise these approaches arriving at packet cellular data from the satellites in the sky, like the weather satellites. They all use JPEG imagery. So it's been a very, very successful standard, and it enabled so much of the continuous tone imagery to get over the bandwidth as of like the internet bandwidth, and then all the tooling that's been attached to it. It's very ubiquitous and common, and quite so much the standard. And then also, although not all of its aspects are unencumbered by the intellectual property or the patent laws, that only usually leaves out arithmetic coding of the JPEG-LS, a lossless profile of JPEG, and that might have by now fallen out of patent protection. Patents live for 17 years, or 21, some say. It similarly is with regards to GIF or GIF. Some people say GIF, but I would say GIF, the graphics interchange format. That had a patent attached to it, the Lempel-Ziv, lossless, some run length encoding, plus a bit of some Huffman coding, and then it arrives at that's pretty much it. That was where Huffman coding is not patented. It's obvious to practitioners in the art. It's not patentable either. That these days, instead, there's PNG, portable network graphics, which are another lossless profile that's suitable for document images and media elements. These would be something like scalable vector graphics, or SVG. That's instead of these are raster representations, meaning like a rake. It's a bit map, so it has rows and columns, and the picture elements, the pixels. These are raster images, Then the vector images, vector procedural graphics, are another way to make graphics, like scalable vector graphics, which is a great little format that's based on XML, and then just has procedural elements for drawing elements. Usually Notion is called the canvas, and then to paint on the canvas, or to draw on the canvas. And then there's other kinds of ideas that get involved. There are JBIG and JBIG2. So this is for the joint bi-level imaging group, or joint black and white, monotone images, document images usually. And so these have then those are some encodings, and they have like the list of many hundreds of different little patterns. So that then when there's repetitions in those patterns, like with Moire or whatever, it can basically then have an encoding for those. Kind of like TIFF or facsimile G3, G4 compression will have given runs and the verticals, and then the Huffman coding already haven't been kind of found for those, the alphabet, that are after the reference implementation and specification. Then those kind of match the corpus of the data that's so compressed. And so that thusly it's kind of like this thing. So JPEG is a lot more adaptive than that in some senses. And then it has various notions of the transforms on the data to basically separate it into two components, and then to compress those separately, because they'll be much more compressible each in the other than as composed. Then they get recomposed. So then that gets into these are kind of the encoding methods for the compression, and then they're used in many other file formats, like any of Apple's imaging file containers. Any number of them use JPEG, or all kinds of EXIF and camera file formats use JPEG if they're not RAW or something like that. And then there's TIFF, the tagged image file formatted container, for otherwise facsimile compressed data, or JPEG compressed data, or Deflate by the algorithm, the PNG style compressed data. So that there's a file formats, like when you see a JPEG file, it's really a joint JPEG file interchange format, JFIF, JFIF file. So the file is actually called a JFIF file, but nobody says that. But they just call it a JPEG file. But it always is contained in these markers or segments, and I'll have to look and recall exactly what the terminology is, because the idea of this in the file format is that as just some forward array of bytes, that it starts with the markers are of a given fixed alphabet. They're defined by these standards. There's a series of about 6 or 7 standards for JPEG, a couple more kind of in the middle, and then 10 or 11 for JPEG2000, which is not so widely adopted at all. JPEG is everywhere. JPEG2000 is very widely used in a lot of different media profiles, but as far as the image files themselves, the still pictures usually, it's still all JPEG. And because JPEG2000 also has some more patents associated with it, the intellectual property. And MPEG has what they call, like the MPEG-4 has their intellectual property stuff is made in kind of in a fair way. And so it costs money to implement stuff and use MPEG-4, but it's at least kind of, it's not deemed like patent trolls and these kinds of things. So anyways, getting back to the file interchange format and how it begins is just a sequence of bytes, just like any other file. It's got a beginning, and then considering it doesn't have any sparse extents or gaps in it, that being a thing sometimes, but usually nobody thinks that that's a thing. It goes from the very beginning to the very end, always a sequence from beginning to end of these bytes. And so a pair of these bytes together make a number between 256 squared, between 1 and 256 squared, because each byte has got basically 1 through 256. So together, just like 10 and 100 can make 10 squared, then these 2 bytes make these 2 codes. Now, the hexadecimal codes of these, or I have to think that it makes 256. Excuse me, I'm thinking of a 32-bit integer, say, and I'm very familiar with the arithmetic, but just the point goes to show that these things are like so, that the hexadecimal character pair will be like F is 16, so this first byte will have FF is 255. So 0, then 255. All right, so yeah, these 2 bytes then make 256 squared possible combinations. And then what it has usually is just the first marker is just a constant, a few ones, and then the last one is the specific code of the marker or the tag, the segment, sometimes in file formats is called the chunk. These are names for these different pieces of the file format. When you don't have fixed length sections, like this header is 48 bytes and it's just a string that says the name, and then follows some data. This is variable length, these segments, and so it'll start with this marker, and then the next 4 bytes is always the length of the rest of the chunk. So as reading along, then you say, okay, this is my kind of chunk, according to that type of chunk, and then they're all kind of the same. It's like this is how long the length is in it, and then this is the data that gets stored in these kinds of chunks. Then as it's reading forward, it will find for these segments or as tags as beginning of these or the markers sometimes they're called, then these pieces of data, which I should be able to find from that, because the JPEG-2000 uses pretty much this same format as JPEG, then gets into these different kinds of things. So wondering about that a little bit, this is a book by Taubman and Marcellin, and so when JPEG-2000 kind of came up and out, then this was the thing. And so I was studying this when I was working on it like in the early 2000s, and then in 2005 I was working for a fabless semiconductor chip outfit. And so what they were working on was a JPEG codec, because digital cinema, like in the movie theaters, was going to this at the time. So the idea was to implement a chip that would make it possible to encode, to compress data into JPEG-2000, and then to decode and decompress, to take the JPEG-2000 compressed data, make it into the raster bitmap, so that in showing it on the screen, then it would fit in the matrix of the grid elements, of the picture elements, the data. So let's see if I happen to have this other one in the same box, because that would just be relevant as well. Maybe it's in there to be found somewhere. If not, it's in one of the other ones, because it's a giant pink book is what this JPEG book is. It's just this giant pink book called JPEG. So these are not it. I'll get to it a little bit later. But JPEG-2000 then is this book, and it's called JPEG-2000 Image Compression Fundamentals, Standards and Practice, by Taubman and Marcellin. Taubman was out of the University of New South Wales in Australia, and so he's the main author of this book. He also wrote a reference implementation of the software in portable software. Because one thing about JPEG, and one thing that led to its great adoption, was this one fellow wrote a library called LibJPEG, and it is used in so much open software that renders JPEG images that was just the standard for a long, long time. And any other package that uses JPEG images, almost indubitably, unless they wrote their own JPEG software, which is possible, and I've written pieces of it. For example, it is part of verification of the chip, putting that together. And it's very much designed to be implemented in hardware. And these kinds of things. And one of the fellows in that group was also associated with the standards processes and protocols. And I've been kind of associated with the standards process and that back in the 90s with MPEG and stuff, but much more peripherally. So that this is kind of like how these things are made, so that then everything today runs on it by just kind of this group of engineers that do the right thing to get all this stuff put together. And then that there was an unencumbered reference implementation like LibJPEG, then made it possible for its very ready adoption. So this book gets into image compression overviews, elementary concepts, digital images, lossless and lossy compression. Lossless, of course, just means like whatever you put in, it comes exactly out the same. And lossy compression, like all JPEGs pretty much are, it's like put in this data, we're going to transform the data, we're going to compress the data. We're going to do this in ways that, according to this theory and according to people's perception of then when they see it, when it's rendered, it doesn't look any different. It's as high fidelity as it can be, the lossy precision. And so it can be compressed also progressively. And one thing that this book gets into is like different levels of the compression in one file format. So it like starts and then grows progressively more refined as it has more data that can load, where I can just start with like at least a sample of the image and then grow to fill that in. That the lossy compression then also makes it's not possible to make round trips, because if you get a lossy compression, then take a snapshot of that, compress it again, take a snapshot of that, compress it again, and so on, it will eventually lose data, and then artifacts, is they're called, things that don't belong in the data will start to appear. So these are the kinds of things that go into lossless and lossy, which then affords that it fits in the bandwidth that otherwise it would take much longer than it would be possible to have to send the imagery. Measures of compression, that's kind of like the ratios and these kinds of things. And then it talks about exploiting redundancy, statistical redundancy, and irrelevance. So exploiting redundancy is here it's called like the Huffman coding. And so there's run length coding as like there's the first line is 100 white spaces. So just write one white space times 100. Run length coding is like this run of spaces is 100. The run length, you encode that. It's got one of these codes that sits out from otherwise just the samples, where the sample is out of the color space, the red, green, and blue, or here it's almost always luminance and then red and blue chrominance, luminance, chrominance, LCC, or YCbCr it's called, Y for the luminance channel, and chrominance B and chrominance red. Those colors put together as a sample then make it so that that represents the image, without getting into stuff like all the different color models and sRGB and these other kinds of ideas on what's on the display side, vis-a-vis the luminous, chrominance as how the image data is captured, and the translation functions, transfer functions, usually enough, between these color spaces, elements in the color spaces, that the samples would be the raw data. If you were just going to say, my file just has pixel 1, red, green, blue. Each of those elements, say from 0 to 255, 8 bits red, 8 bits green, 8 bits blue, a 24-bit sample in red, green, blue. Compared to like a palletized sample, which is like, we have 8 colors. Maybe there's 16. Fit them in 3 bits or 4 bits a piece. Maybe there's 556, 5 bits, 5 bits, and 6 bits. That's not unusual sample with regards to something like Windows bitmaps and the GDI graphics imaging system. A very usual thing when dealing with those kinds of images on that kind of platform. So the statistical redundancy could be like that, and then it also gets directly into the Huffman codes. So this is where it's like, well, we besides knowing that maybe it's just got a run of these codes, and so you could estimate what that would be, another kind of subset of Huffman codes. This is the one just says is like the most commonly occurring thing gets the shortest element, or its expectation, and then sends that, and so that thusly it arrives on average that a plain blank image would just have 1 bit per sample all the way through it, if that's just the most trivial code. So it'd shrink, but one that was everywhere, not at all common to colors, then it would just fill that out, to where eventually then it would just be that at least some images are incompressible. There's no way to really compress them. Although after taking a losses on that, then at least some of the data can be thrown away. But for the lossy compression, there's at least one example of an image that's not compressible. So that's just a usual enough thing. So JPEG is a great thing. And then it gets into here the elements of a compression system, the importance of structure, coding, quantization, that's like taking the samples and putting them into bits, and transforms. And so quantization can also involve when taking groups of elements together, like a block of elements, what to make of those, because the quantization is kind of like a progressive, this hierarchical pyramidal view in JPEG-2000, and so that's something else to be addressed a little bit more theory than the idea of sampling, which is quantization itself already. What that means here in JPEG-2000. Transforms, alternative structures. So then chapter 2 is entropy encoding techniques. So about the concept of entropy, Shannon's noiseless source coding theorem, Elias coding, variable length codes, Huffman coding and Golomb coding. So Golomb is another sort of coding, variable length codes, arithmetic coding. So arithmetic coding would be probably most familiar in its use today, is because all kind of these vector machines are using a sort of arithmetic coding. And so that's just kind of to say that to multiply it by numbers, refine until it falls into a particular interval. And then, so kind of exploiting arithmetic up to the point where that arithmetic is still good. So that it's got to be kind of like extended precision arithmetic, or it would just be floating point arithmetic, and how that can maintain its accuracy. With regards to the fixed point arithmetic is maybe usual in these schemes here. The arithmetic coding is just another way to say is like this is an addressing scheme, and it results a shorter amount of data to be written to address, because then on the map that it's consulted afterwards, it's just drawn out of the map, whether it's a color space or after the data is transformed, or according to like the perceptual coefficients that according to studies of vision make more or less sense, that they do or don't adjust the image, or they do fill the perception with that these are the kinds of other approaches and pieces that go into making overall the file format. Well, any one of them by themselves also does compression. And so that this helps go to show that much simpler means of image compression could be without using all this machinery. Yet these are the ones they have there these days. Then other efforts these days have been trying to take it away from like this group in the International Standards Organization, the ISO standards, and what are also the International Telecommunications Union standard, and make them usual consortiums, they call themselves, say, or not standards bodies though, we call them, but companies just trying to sell their research, and usually that it's encumbered also. So trying to exploit, as it were, the economies of scale, and to get people in the ecosystem. They all follow these sorts of approaches because all they learned as an example of having to do all this kind of stuff was like so. So WebM or movies, many of the different Apple multimedia formats were before this. So that encompasses a lot of different things because that was a usual platform for storage and a lot of these things that went on with this, with the digital cinema data. But then this is after JPEG became so totally usual for continuous tone imagery and the lossy, the notions of the transforms, and then the compression after that. That it is the way of things for sure. Arithmetic coding, image coding tools, context adaptive coding, predictive coding, run length coding, and quad tree coding. So the quad tree coding was kind of mentioned as like the layering, and that it's related to the quantization. I think it was, but I'll have to look at that. Run length coding, predictive coding is basically is building an estimate over some time, given that it's like to sow a given run, then whether it's expected to continue according to what aspects of a distributions you could encode in one of these segments and then indicate by one of these values. And so when it shows up, the decoder can say, all right, this is going to result these bits, making a sample, rendering that to the output device. Quantization. So quantization is all of Chapter 3, rate distortion theory, scalar quantization, differential pulse code modulation, vector quantization, trellis-coded quantization. That's kind of what I was thinking of this trellis coding bit. Because what that gets into is a way to write like these zigzag components. And so when they show up, then it kind of makes a template. And so that then the mathematics can be a big block and a vector, and then just roll all those samples at once, kind of a thing. While it also supports it when it's like looking at from different levels of perspective and so on. Image transforms is Chapter 4, linear block transforms, subband transforms, transforms for compression. 5 is rate control techniques. So rate control, as you might imagine, is really about like bandwidth accommodation, because the idea is there's only a particular rate that's possible according to the bandwidth. And so then the rate control is about how you can encode the data so that it will arrive at a given amount of bandwidth. And also then rate control, you can consider as like, well, how much of the image does it deliver? So rate control also involves bandwidth, and also involves quality, say, too. So that gets into, it says more intuition, optimal rate allocation, quantization issues, distortion models, refinement of the theory, adaptive rate allocation. Now chapter 6 gets into filter banks and wavelengths. So filter banks and wavelengths is all the transforms, because in the JPEG standard they got what's called the cosine transform. So after like there's 2 transforms applied. It's one's for the lossless part, and then the other one's for the lossy part. So the discrete cosine transform is lossy, it's used for that. And then in the JPEG-2000 there's the discrete wavelet transform, and then there's also one that's a lossless profile using the wavelets as lossless. So this is about then the wavelet theory. So the cosine transform theory is something to be read on a little bit and be refreshed, because it's used in a lot of different places. And we think of stuff like in mathematics, like Fourier transforms, and then like cosine transforms, your wavelet transforms, Henkel, Mellin, Z transforms. Any pair of orthogonal functions makes its own transform, and then it's usually used for things like frequency and time, and then also for like different bands in the color spaces in the colors, different lines in the spectra of all these different things. That here it's figured out that the wavelets then have, according to this development, has a very direct implementation in hardware. Digital hardware, and then the result that it fills out these things. See, classic filter bank results. So that filter banks and ideas like the Kalman filter and some of these other circuits that are implemented in digital electronics so often. It has that this is involved with that. That from like a software perspective, it might be like, why would I need that? I mean, I just have samples already. It's like, well, it's got to come from somewhere, and so this is kind of how it does. Wavelet transforms, construction of wavelets, lifting and reversibility. So reversibility is about the existence of the inverse of the function, say. And then lifting gets into other properties, aspects of the data under these functions, where it's possible to consider different regions or segments or perspectives or perspectives or the focus, these kinds of things. Boundary handling, what to do with the edges, the edge and corner cases. Because when you think about something like Fourier analysis, you might know that there's the Gibbs phenomenon, the ringing at the edges. So that a Fourier analysis makes for so that, like, well, you can take any polynomial formula, a wavy curve, and represent it as a sum of an infinite series of periodic functions that are only oscillating regularly up and down and as they go along. So a given number of those by these coefficients, and the Fourier analysis makes it on the edge of that are these Gibbs ringing, and so it's known that there's a particular quantity that has that at the edge of the corner and the boundary cases, it runs off. So then trying to figure out what to do, how to basically just get that part in the middle, has to do with things like sighting and cosighting and the picture elements, and then finding the rendering area, and then furthermore with regards to these transforms, what to do about the edges, or in this case boundary handling, signal extension, symmetric extension, boundaries and lifting, further reading. 7 is just zero tree coding. So this is part of the scheme that builds, because I think it relates kind of to the quad tree encoding and making the whole pyramidal possible, so that you can start with a segment image and the different blocks, because as JPEG comes along, it comes along in little blocks, and they're like 4x4 to 16x16 to 64x64. So when you think of a raster image, it's just like a row, a scan line, and then the next one, and then the next one. So similarly, so with JPEG, it's like a sequence of blocks, a sequence of blocks, a sequence of blocks. Each row of these blocks, scan lines, you'd say, except these having more than one picture element or pel or pixel piece. Then it's just these blocks in the order, in the rendering order or in the scan order, it would be called. Because this sort of imaging format supports multispectral imagery of all sorts of raster imagery, and then some aspects of overlays and stuff like that, but mostly only this pyramidal aspect that makes it possible to zoom in on a piece of data. For example, to know where in a file where it begins, to look at a map and then to zoom in to a piece of data and to know where in the file that would be with a higher precision, all this raster imagery. That's what's then part of what's described as zero tree coding, which is otherwise just a way to like take this block and then put it into these bits so the decoder runs them right off, and then that's a very direct thing. With regards to that's a little bit more of a feature in JPEG-2000 than JPEG. And so I would like to have the JPEG book side by side with this, compared to the JPEG-2000. At some point in time, of course, I bought the standards because I had to read them, and so it costs about $100 to get all the standards for or copies of all the standards for JPEG and JPEG-LS and JBIG and then JPEG-2000. I think I had copies of those one time. The ISO will or would give several free copies to researchers and students, and then after that, though, that it does cost money to get the actual requirements for implementing all this kind of stuff. That's the kind of thing that is expected. That this kind of book is above that to help explain all that. The specifications are amazing works of declaratory instruction. The specifications are so awesome that come out of these things to be able possible to recreate objects meeting the standards. So this is then just a really fantastic book to understand all this detail and what's going on with it. So we've got EZW and SPIHT. This is another encoding mechanism for this zero tree compression. Chapter 8 is highly scalable compression, embedding and scalability, optimal truncation, embedded block coding, abstract quality layers, from bit planes to layers, experimental compression. And this reminds me of there's another file format called SPIHF, SPIFF, SPIHF. So JPEG-LS and SPIHF were related, and SPIHF is another. I think it's a lossless sort of format, and it wasn't encumbered, and SPIHF is good format. And so that's part one of this book, and then part two is the JPEG standard. So this was about like encoding and decoding and compression and decompression and some things to do about imaging. So then part two is about the JPEG standard, JPEG-2000 standard. Says introduction, sample data transformations is chapter 10. Chapter 11 is sample data partitions. Chapter 12 is sample data coding. Chapter 13 is code stream syntax. So if you recall the idea of the markers and all that stuff, and it's like, what is in that file from where it begins? What is in it? It's code stream syntax, and so then of course those are the markers, those tags, and the marker segments. They're the bodies that so follow those. And so basically the JPEG-2000 marker segments are distinct from the JPEG marker segments, but they all still fit in the same alphabet. So machinery and software that works with like these kinds of chunks and tags can still go through the image and find all these chunks and tags in them. And then according to what metadata may be in them, like the EXIF metadata from the photography people, the cameras, that it's got the location and the time and maybe some metadata that is associated with the image. Besides the imaging itself, it's got these kinds of things. It's also got stuff to do, for example, with rights and authority. Whose picture is this? And whose copyright is this imagery and that kind of stuff. But mostly, getting into the tile parts and mains. The idea that JPEG and JPEG-2000 are tiled image formats has that most usual idea of organization. An image file is lines, scan lines, and then those are like in stripes. Sometimes it's said, and so then tiles is involved separately because a scan line has a given length, and then it has like according to the bits per sample and the width of the line, and how it can be represented in an array, and then the addressing of that, and then the edge cases and the corner cases, where edge cases and corner cases themselves were named just from handling images and raster imaging. So every time you've ever heard happy case, what they're really talking about is like it's not an edge case or corner case, which is really from this study in this field about the stride of the samples and the area, and then a couple different words can end up like the stripe, and then like the streak, like collected scan lines, and then stribe is this last word that fits with stride and stripe, and a streak with a Q, S-T-R-I-Q-E, and then stribe, S-T-R-I-B-E, that these represent 4 arithmetic quantities that I made up to put those together because that way they just fit together in source code. Nobody uses that, but everybody should know stride at some point because that's kind of like the bit stride, they call it, or it's with alignment and stride. So these are the kinds of things. And so tiles, then it just reminds me of implementing some of these parts to do with like the tile parts and stuff like that. Because just like the edges and how to handle the boundaries and stuff like that is like, this is where they are. This is all the arithmetic that then gets this related to whether 0 is on the lower left or the upper left. So this is top down, left right, or left right, top down, or any of these other possible orientations of the rendering as sequential, the rendering as an area. So often the orientation of an image will be represented by the letter F from English, because the letter F, according to different orientations, has 8 orientations, but it's the only letter in the alphabet that's asymmetrical in this way, so you can actually tell it apart by seeing what it looks like flipped. So the 8 orientations of imagery orientation are usually indicated by what the letter F looks like. So then, chapter 14 then is the file format. So this code stream syntax are like, these are the chunks, the marker segments. The file format is the structure of a box. Oh, and the JPEG has the JP2 boxes. So it's kind of got boxes have chunks or marker segments. They're encapsulated in this way, just like packets are encapsulated. And indeed, this is supposed to fit again with networking and packet delivery and this kind of stuff, packets. These are the kinds of things. Then chapter 15 is extensions, and so some options. And then part 3 says working with JPEG-2000. 16 is performance guidelines. Subjective comparison of JPEG-2000 with JPEG is 16.1.3. 17 is implementation considerations, like ideas and suggestions and warnings. It's like, this is just got to be done this way. These are the costs. Numerics, structures, system considerations. 18 is compliance. It's like conformance and compliance. And then part 4 says other standards. 19, JPEG. That's all it says. JPEG is a rather shorter specification, but it's everything that's in JPEG is pretty much also present in JPEG-2000. Not exactly the same, but a lot the same. So implementing these things comes as after this, but really just to get a copy of the standards, because then thus they'd be like so. Talked about gain, band factors, factorization methods, the FIR filters, the FIR filters, the FIR and IIR, the forward and inverse IR filters, Dobitsch's CDF97 subband wavelet transform. It's not necessarily know all the theory usually to implement the hardware or the software, but this helps go to show what goes into making this, like, to how these things can be So yeah, this is a fantastic book, and it's got a lot of the mathematics and the theory behind what otherwise is in the standards. It's kind of like, you know, A slot B symbol, you know, and this kind of thing. Filter banks. In filter banks and wavelets. In this section, we review some of the classic results in the development of filter bank theory and subband transforms. So it is, when first encountering this material, it's just like input what output, and so filter banks then get into like this is a way to apply stuff in parallel, like it's got a wavefront, you apply it to the filter bank. And it's got like rapid detectors, and so it's all about the Kalman filter usually, Kalman, Kalman filter in electronic engineering. Subband transforms is like, well, we got data in red, green, blue, or maybe it's from a satellite up in space. It's got 38 different cameras pointed at the same picture, each one sending down their infrared or ultraviolet or this, that, or the other bands. So how do we put them together and take them apart? And these transforms, while keeping them together and being able to put them back together, subband transforms, which can all be considered like a band transform. And then it gets into like ideas of like filters and band pass and high pass, low pass, and otherwise what happens with noise and signal. Though this is about usually the transform filters and the filter banks, filter taps, banks, these kinds of things. As the author notes, the reader is encouraged not to gloss over this material since it provides a foundation for intuition concerning subband transforms. The synthesis system must perfectly invert the analysis system of a subband transform. Equivalently, the analysis and synthesis vectors sequences must satisfy the biorthogonality relationship of equation 4.29. Moreover, our development of subband transforms began with the natural generalization of block transforms to convolutional or sliding window transforms, or sliding window transforms, showing that these are equivalent to filter bank systems. While convenient for the present treatment, this is not the historical sequence of events. It's laid out here as like the classic events as they were discovered and in theory and in the field. The convolutional is just being able to use the reflective and symmetric on these things, and then the sliding window is just kind of like, well, when does it line up with something that's its own box, kind of a thing. Subband transforms were first proposed in the mid-1970s for the coding of speech signals by Crozier, Esteban, and Galland, using a special type of analysis synthesis system known as a QMF, quadrature mirror filter bank. QMF filter banks do not generally satisfy the so-called perfect reconstruction, PR property, whereby the synthesis system perfectly inverts the analysis system. The term filter bank here refers not just to an arbitrary collection of filters, but rather a maximally decimated system of filters and decimators of the form shown in figure 4.10, where the combined rate of the subband samples is identical to the sample rate of the input sequence. So establishing that sort of congruence. The distinctive characteristic of QMF filter banks is that the end-to-end transfer function through the analysis synthesis system is that of an LTI, linear time invariant operator. That is, the aliasing necessarily introduced during analysis is perfectly canceled during synthesis of the time and space components, most usually. The introduction of alias-free, maximally decimated filter banks led to the investigation of perfect reconstruction systems, in which the end-to-end transfer function is at most a pure delay. The key results on PR subband systems were developed in the mid-1980s by Smith and Barnwell, Mintzer, Vetterli, that seems to show up a lot, and Vaidyanathan. Some of the classic results of these studies are reproduced below. So this is a pretty fantastic book. So somebody who's looking to implement JPEG-2000 would, they'd probably just download the reference implementation provided by the author of this book and use that. But somebody wanting to make their own would find this a very useful resource. And why one would want to make their own includes ideas, for example, that that's how they want it. That's the way I want it. So that's the way I'm gonna do it. Let's see here. Here's a fun little book. What's this? This is okay. This is something different. Illustrations to Dante's Inferno. So this is Eugene Paul Nassar. Here we looked the other day at something like Dante's Inferno, about the Paradiso and the Purgatorio and the Inferno. So this is just it's just books of illustrations of Dante's Inferno. Here, and there's many different authors and artists over a long time have done many of these illustrations. Here's like from Paris and the Bibliothèque Nationale, Luigi Adamoli, 1817. All these animals and beasts and tortured figures. Stratinus, John van der Straat, 1587. Laurentian Library, Florence, 1481, 1478. Botticelli, Jan d'Argent, 1879. Manfredo Manfredini, 1907. Bartolomeo Pinelli, 1826. Gustave Doré, 1861. The Biblioteca Angelica, manuscript 1102, Bolognese, early 15th century. Sandro Botticelli, circa 1478, a sketch. Doré on Dante. Tragedy, evil. Yeats, William Butler Yeats, George Santayana, Salvador Dali. There's many famous artists represented in this volume. Oh, here's that Strogatz book, The Infinite Powers. Yeah, I was going to read this again. I got into it quite a ways, but he's talking about DNA or something like that here. And so it's because it's about the infinite. What I'm interested in is the superstandard and extraordinary. And since it doesn't quite arrive to that, then it's just kind of like about convergence, because it's from the perspective of a guy who knows a lot about real analysis. And so when I'm reading something like Strogatz's Infinite Powers, and I'm going to look at this again, because it's been some time since it was published, and it was kind of first read here in 2019. That this is about calculus then. Powers of 10. Here's like the first three powers of 10 are numbers we run into every day. So yeah. Constant acceleration. Here we got like the whole infinitely many higher orders of acceleration in the moment in motion bit. Scholars in the Middle Ages already knew the answer. William Heytesbury, a philosopher and logician at Merton College, Oxford, solved the problem of around 1335, and Nicole Oresme, a French clerical mathematician, elucidated it further and analyzed it pictorially around 1350. Unfortunately, their works were not widely studied and were soon forgotten. About 250 years later, Galileo demonstrated experimentally that constant acceleration is not a purely academic assumption. So this is about constant acceleration. Yeah, the infinitely many higher orders of acceleration is any non-constant acceleration. That any change at all must be. It's unlinear. Next, knowing that the speed grows linearly according to v equals at, how does the distance grow? This is usual. All right, so this has got coverage of these kinds. Newton and Kepler's law, rigid body dynamics, Kovalevskaya. The insolvability that Sofia Kovalevskaya discovered is related to a structural aspect of the equations for a top, the gyroscopic. The equations are nonlinear. The technical meaning of nonlinear need not concern us here. That's with regards to like the linear and the ordinary, and so it's kind of it's a little bit underdefined, but it basically means not modeled by systems of linear equations, but it can include any kind of a number of other kinds of things, because anything that's not modeled that exists empirically is just like, well, it can't be linear at that point. So it's the nonlinear and the unlinear are two different kinds of things, because the unlinear is just the declaration is like, well, formally the account is it's only linear at the end. It's not linear from the beginning to the end. It's only linear at the end. And then even if we start with a linear, there's the unlinear and then the superlinear, meaning it's like, well, yes, everything has like cause and effect again, and it's all matters of a perfect reflection in the potentialistic account. But that's a different kind of story that has been covered here quite a bit. Yeah, so I'm going to look at that. I'm going to look at this again, but I just because then he's what he's getting into is like alpha infinity, alpha zero, and deep mind. About like, well, what happens when we just throw enough computing at and it's like, well, it's a giant finite element analysis until it's worked out that it's analytic. The Riddle of Gravitation. This is a fantastic book. Peter Bergman's The Riddle of Gravitation is awesome. Now, I need to recall why it was, but I remember reading this and finding something that was like, that helped make my mind. And it's probably when I was first, considering the ideas of fall gravity. It's like, well, how could gravity be a part of the theory without it being owing an explanation? Why does so? So this, though, is Bergman's is a pretty great book about the riddle of gravitation. Schwarzschild's solution, Minkowski's space, Schwarzschild, Minkowski, redshift dependence on distance. The mass of a stellar object is sufficiently large. So yeah, Bergman here is pretty well informed about theories of gravitation and physics. In this thought-provoking book, written for the layman, a noted physicist offers a fresh, non-mathematical introduction to the conceptual foundations of both Newton's and Einstein's theories of gravitation. Anyways, this isn't a bad book. It's got a great glossary in the end with many definitions that would be sound. Sound. Yeah, besides video data, and then there's also audio data, and then trying to figure that out as its own kind of thing. When I was a child, I taught myself how to whistle, because well, it's a skill, and it doesn't take any money or any equipment, so it's something that, absent other money and equipment, but nothing but a lot of free time and initiative, is possible to entertain. Not much to it, I know, but yeah, I could whistle about almost an octave and a half, or almost 2 octaves sometimes. And then the key thing about whistling, and it's just called whistling, compared to like the other forms of whistling that involve making a chamber that sets up the resonance and this kind of stuff, is that the whistling can be accomplished inhaling and exhaling. So it's not necessary to ever stop whistling, because you can just continue whistling, inhaling and exhaling. Whereas when speaking in the spoken word, that's almost entirely exhaling. So it just kind of requires the ability to just take a quick breath, these kinds of things. So that's just something to mention with regards to sound that I thought would be of interest, because it's just one of these skills that then isn't so much useful for things later. But some languages are actually built on clicks and whistles, and human languages, or incorporate their elements, or that it's used as for distance, and that it's piercing quality, and otherwise its tone carries. And also it is for making the animal noises, as like those of birds and mostly birds and these kinds of things. Whereas the formation otherwise of sounds that animals vocalize, like cats or hoofed animals, or these kinds of things, that's a different kind of skill. And I didn't have you know, that I didn't grow up in like in a farm type environment, you know, and with like a speak and spell or see and say or these kinds of things that was so relevant. Although we definitely did have see and say and speak and spells when we were growing up. The speak and spell particularly was actually a really important thing for a lot of people to get them into spelling. This is just cultural references, not so relevant to everybody. But then that's what I want to mention about that. Yeah, the whistling is exercise then, because then it can be very much just what's the word? Not random, but just simple arrangements. It's on demand. Say it's on tap and on demand. So I can readily whistle for like 15 or 20 minutes, and it won't be the same twice. But it's kind of musical somehow, and that's just usual thing. And so whenever there's needed a matter of entertainment while doing something otherwise as the drudgery, or like taking a long walk, or just to fill the air, or something like that, it's a skill learned. It's so long ago that long since my voice went from like 3.5 octaves to like 2.5. But a little bit lower, but a lot less higher. So the whistling is about the same. So these are the kinds of things. Yeah, I used to have at least a 3.5 octave voice and pretty good to control, but now it's just mostly all the spoken word bit, which is acculturated by practice and theory. Well, then a few minutes left. We'll look at D.R. Cox's analysis of binary data from Methuen's monographs on applied probability and statistics. So this is nice because it's about binary data and it's about probability theory. So other books along this are like Theory of Road Traffic Flow, Stochastic Population Models in Ecology and Epidemiology by M.S. Bartlett. So Ashton's Theory of Road Traffic Flow, Stochastic Population Models in Ecology and Epidemiology by M.S. Bartlett, Renewal Theory by D.R. Cox, The Statistical Analysis of Series of Events by D.R. Cox and P.A.W. Lewis, Cues by D.R. Cox and W.L. Smith, Monte Carlo Methods by J.M. Hammersley and D.C. Hanscom, Time Series Analysis by E.J. Hanan, Analyzing Qualitative Data by A.E. Maxwell, Empirical Bayes Methods by J.S. Meritz, The Theory of Storage by P.A.P. Moran, Theory of Random Clumping by S.A. Roach, The Foundations of Statistical Inference by L.J. Savage, Stochastic Processes by L. Takacs, Sequential Methods in Statistics by G.B. Weatherall. So this is from the United Kingdom, as one might assume. In UK only, £2. It has several marks of ex libris on it, besides what would be mine. It's 1970. Distributed in the USA by Barnes & Noble, Inc. Now, I went to a Barnes & Noble the other day, and there's nothing, I couldn't find anything really like this there. But there was a time where it was like, that would be as good as like, the other scientific bookstores. Like, usually they'd be found in like largest cities. Scientific bookstores are where to find this kind of thing. This monograph concerns the analysis of binary or quantile data, i.e. data in which an observation takes one of two possible forms, e.g. success or failure, or bits. The central problem is to study how the probability of success depends on explanatory variables and groupings of the material. So a lot of the stuff that goes along with the predictive coding and these kinds of things is kind of related to this kind of account. Many particular methods, especially significance tests, have been proposed for such problems, and one of the main themes of the monograph, these methods are unified by considering models in which the logistic transform is related to the logistic model and the log logistic. The logistic is a very usual setup in dynamical modeling with regards to population models. of the probability of success is a linear combination of unknown parameters. It's a linear combination of these. These linear logistic models play here much the same role as do normal theory linear models in the analysis of continuously distributed data. So this would serve as kind of at least an aspect or part of what goes into the log logistic and the linear logistic, as it's put. So something for to be read at some other time. The hour is upon us then, and I so hope you've had a great day. Or if this will be any use for you, it's just kind of an introduction and is a talking points, kind of about what JPEG is and what its requirements are of the internals. That's mostly the internals of the data format, and then as with regards to its file format. And so then with regards to imaging file formats and data formats, they all are files, and then the idea of segments or chunks or header and body or header body trailer are ubiquitous in all sorts of data file formats. Have a great day. Goodbye.